I'd like to talk about that.
I actually
Yes.
will. Can I do a real follow-up question?
Please.
You said something, Ryan, inside your talk, which is how do steps work? And I thought the same thing. I'm like, how do magnets work? How do steps work? And so, can you explain why that's such a tremendous problem?
Yeah. So I don't know what a magnet is exactly. Maybe.
Yeah, no one.
You
does.
don't have to answer that one. It's
Yeah.
not possible.
This is not going to be. We don't want this to become a Christian stream right now, so please don't answer that question.
They don't know the reference, Brian. They don't
Okay.
know the reference.
No, he does know the reference. That's why he said that.
No, I don't think he knows the reference.
Take a look at this fine creation and enjoy it better with appreciation.
I don't think I know.
Magnets work. He doesn't know. That's fine.
Oh,
Neither
really?
does chat. Move on.
Okay, got it. Okay,
we
I think
killed him.
that.
Well, that was the
Oh.
perfect response if you did know, though. That was, so good, because we don't know how magnets work. I mean, no one does, right? That's the whole point.
Yes.
I see.
Thank you, Casey.
I see.
All right.
Okay,
All right,
so
let's
I
get
can
off
explain
theology,
how.
Let's get back to this. How do steps work?
Okay, so line stepping is. Okay, I guess the first thing to understand about the problem of stepping is sort of how a debugger interacts with another running program in another native running program on an operating system. So basically the debugger has the opportunity to make changes to memory and make changes to registers, and then it can suspend or resume certain threads. You can basically set up certain threads to run or others to not. And then it just says go, basically. It can just say to the operating system, okay, now you can schedule this program's threads again. And then the debugger loses all control at that point until that program does something that would cause the kernel to transfer control back to the debugger. And so if you think about what it actually means to step over a line of source code, first you have the problem of locating where the where a thread's instruction pointer, because you're stepping a thread over some line of source code that it's on. First you have to extract the register value that stores the instruction pointer of whatever thread you're stepping. You have to then understand where that actually what source code that actually maps to. Once you know that, you know the range of addresses that are associated with that particular line of source code that thread happens to be stopped on. And then you have to say let me, basically I have to produce the effect that this thread will stop execution, the program will stop execution when this thread leaves this line of source code. Now, a very naive algorithm you could do to do that would be to say there's something on CPUs where you can single step a thread, which at that level it's just stepping over one single instruction, and then it immediately interrupts. So you can basically set a bit in one register on the CPU, and you can say, okay, step over one instruction and then stop.
Can I interject one thing real quick here for the folks at home? So just to be clear for anyone who hasn't looked at this kind of thing before, so when you have a line of source code, a compiler is turning that into potentially many assembly language instructions that will actually be executed by the CPU. So there's this mapping, and not only is it a one to potentially many mapping, meaning one line of source code could produce many assembly language instructions, but also in more sophisticated builds, like when you're running an optimizer, those assembly language instructions do not occur in a chunk. So it's not going from one to 3 instructions in a row. It could be going from one of your source lines to several instructions peppered throughout other instructions it has been mixed with that come from other lines of source code, right? Yep. So the mapping is very messy, and one of the reasons that debug information is not a super easy problem is because the whole point of that thing that Ryan was talking about before with PDBs and dwarf, this debug info that gets produced when you build your program, one of the reasons that's so messy is because that is trying to store in some way that a debugger can use, among many other things, how do you go from a line of text that the user typed into Vim, right, to which assembly language instructions the CPU is going to execute, which ones it caused, because when you're going through an optimizer, it's combining instructions, it's removing instructions, it's reordering instructions, and so even just that one part is messy. So everything's Ryan's talking about now when he's saying how do you go from one to the other, just keep in your head that it's a very messy mapping between those two. That's all I wanted to throw in there.
I had to also throw in just a quick question to answer along the way, which is when you breakpoint or you hit some sort of stopping condition and you're in the middle of a line, does that ever happen as well? Where you're just I'm halfway through a line, what line do you appear on? Does that screw up debugging information that causes confusion? I'm very curious about that.
Yeah, so that definitely does happen, and it can even happen, like, for example, if you step out of a function call, like, you're inside of a function, you want to return to whoever called you. Generally, like, there might still be some instructions to execute after you've actually popped from the call, so if you do a step out operation, you'll end up in the middle of the line. You're not just at the first address of the line's source machine code. You might be at some instruction in the middle. And so, basically, that's just an extra wrinkle in the problem. You don't, it doesn't really screw anything up, but you just basically have to say, like, this is a range of instructions, and if the thread ends up anywhere in here, I have to associate that with this particular line of source code. So it's one detail in the mapping, but it's not like a showstopper by any means. So yeah, if you wanted to step over a line of source code, if you wanted to, like, basically proceed this thread until it has exited this particular line of source code, you, one simple thing would be to single step that thread until you see it has left the line. Like, you just keep mapping the instruction pointer every time it comes back. And then if it leaves if it's changed the source code line that it's on, then the step is done. So that's a very simple algorithm. It also is enormously slow, because remember that each one of these interrupt instructions that comes back, each one of the single step after a single step has completed, basically what's going to happen is the kernel is going to schedule that thread, and it's going to say, okay, execute one instruction. It's going to immediately trigger an interrupt. The kernel will then it'll switch to the kernel, and the kernel will say, okay, now I need to report this debug event to the debugger, so it has to transition, it has to context switch over to the actual debugger itself. And so every single time you do a single step, it's one of these round trips. You can think of it as between the debuggee or the target process and the debugger itself. And so if you've got a line that has 100 or 1,000 instruction, I mean, you know, you can make it arbitrarily long, really. You know, you're causing a round trip every single time someone every single instruction within that line. So that gets very slow. So instead, what you kind of want to do is say, like, I'm going to set up a bunch of, there's another concept that I should introduce, which is the int3 instruction on x64, but there's equivalents elsewhere, where you can basically put it's a 1 byte instruction that you can use to overwrite any instruction, basically, because it's just 1 byte, so it's the minimum instruction size. And you can go ahead and say, I'm going to put this here, and then when the thread executes this instruction, it's called an int3, and when it, there's other kinds of interrupt codes, but int3 specifically is this 1 byte instruction that you can put anywhere in the code stream. And when a thread executes that, it'll immediately interrupt. So it has the same effect, sort of, as the single step, except it's caused by an instruction you put in the code. And so then so in order to avoid all of these round trips, what you can start doing is saying, when the thread is in this line, and I say step over this line of code, I'm going to basically set up an int3. It's called an int3. It's also called a trap, is what people call it. So what you can basically do is start putting these traps anywhere you think the thread might go within this line. Now, if it's pure linear code, like it's going to do a bunch of mobs and then an add and then, you know, whatever, very simple linear code, there's only one trap you actually have to place, which is at the beginning of the next line. But it starts to get more complicated if you, for example, if inside of that line of source code you've got a jump instruction or a call, then you have to start thinking about, like, where are all the places this thread might actually go to? And so then you might have to start doing things like, okay, let's disassemble the line, let's figure out, like, where the control flow will lead to in this line, and let's go place traps in all of those places. And then it gets a little bit more complicated too, because, for example, if you're in a recursive function call, like, so two variants of stepping exist for people who haven't used debuggers. There's step over and step into. There's a lot of other steps you might imagine doing, but those are the two, like, common ones, and step out. Step over will basically, it won't follow call instructions. So if you do a step into, you're sort of stopped at a function call, and you want to go into the function call and see what's actually happening inside of the function call. With a step over, you don't care about what's going on inside the function, so you just want to step to the next line and have whatever happens inside the function happen. Now, if you wanted to do a step over, you could imagine if you are in a function that is recursive. And remember, a debugger has to deal with any code that someone could write and feed into it. Like, it has to kind of handle all these cases gracefully. There's lots of recursive code that exists. So if you're stopped at one particular line and it's a recursive call into the same function, it gets more tricky, because if you just place a trap at the next line and then you try to step over, you're going to hit that same trap address, but in one layer deeper in the call stack. So you basically have descended to the next call, hit the same trap, but it wasn't actually a step over. Because the step over, it didn't step over the line, it didn't step over all of the call work that happened. Now you're one layer deeper in the call stack, so there's no way anymore to actually step over that line of code. So you have to get tricky about, like, okay, has my stack pointer changed? When do I update which value of the stack pointer that I want to check against? It becomes kind of basically like a little program you have to send down and say, like, if it hits this trap, do this, and if it hits this trap, do this, and if it hits this trap, then single step here, and, like, it becomes a very complicated sort of state machine that you actually have to implement.
So hold on. Can I get one more? Oh, no, TJ wants it.
I just got just a quick question. I was just wondering, like, on average, what your step count is every day. You know what I'm saying? Like, because for me personally, like, I don't know if this makes me a debugger, like a step debugger or not, but, like, I've got my own, like, walking treadmill now at my desk.
Yeah.
So I didn't know if this is kind of like what scenario this kind of goes on. So I just didn't know how this related to debugger. Does this make me a step-driven debugger? Like, if I'm reading...
you're stepping into, you're not stepping over. And so we're talking about stepping over right now, TJ.
Yeah.
Okay, I'm trying now.
There you go.
See,
Yeah,
like, I'm
that's
trying to step
that's
over
the
now.
harder one to do.
Which one is harder? How do I do recursive treadmills?
You're on an int3 and it's
you
inside
put
the
that
stack.
treadmill on a treadmill.
Oh, that makes so much more sense. And then
Yes.
it's running too.
Yes, exactly.
Right.
I got it. Okay.
Okay,
All right.
Prime?
Anyways, you can continue now.
Yeah,
Thanks.
okay. TJ, how long? Okay, now we have a sub question. Now our stack has been pushed. TJ, how long have you been waiting for that? And also, you have just a black square in your screen.
So
I saw you raise it like 10
immediately-
minutes ago.
Immediately after we started talking about step stuff, I put it into standing mode, and I was getting ready. I had to set up that scene. I did not have the video thing ready before
Wow.
this, so I probably heard about 5% of what Ryan said. But I was so excited for this job.
Wow. Okay.
I was
Commitment.
so
That's
excited for
commitment.
this one.
That
All right.
that is some serious professional level podcasting. All right. All right.
So when it comes to stepping and putting in all these int3s, do you also have, like, because I don't precisely understand how jump instructions work. I believe there are relative and absolute ones. Does that mean you also have to update all the relative instructions around all these places that you put these int3s? Because theoretically you shifted down some amount of the assembly.
So
You're not
actually
inserting.
Okay,
Yeah.
I thought you were dynamically at like runtime being like, okay, like they're stepping next. Let's actually insert some stuff into the program.
You're overwriting it. You're over. That's why it's crucial that in3 has a 1-byte version, because you're romping it over the instruction. One of the things Ryan didn't mention, because he had to mention like 8,000 things, because this is incredibly complicated, is that actually when you put that int3 in there, you have to remember which byte you overwrote, because once you are done stepping, you have to go replace all of those with the bytes you overwrote. So that happened as part of this process.
Oh my gosh. Okay, so does that mean when you literally overwrite assembly, and then when it hits that int, you then have to put back in the correct assembly so that when it executes the line, it correctly executes the line?
Correct.
That's crazy, dog. That's crazy.
I don't know. It sounds like probably debuggers. It's as easy as making a regular CRUD app, guys.
Dude,
I
have
mean,
you seen a banking app though, Ryan? Do you have any idea about a banking app?
Yeah.
Yeah, I can't even imagine. It's just...
That's like magnet level stuff right there. The banking app.
yeah.
How
do
do
they
banks
even
work? Actually, we don't know.
Actually, if you would have been paying attention to Twitter, Lori Wire just tweeted how AHC works, which is literally FTP. So
Yes.
All right.
we
there
do
you go.
now know
Cutting
how
edge.
banks work.
Yes, we do. That's why anyways.
So
I'm not gonna get distracted.
underlying all of this, right, is like this is also why you may have noticed there was a little snippet of Ryan at the Better Software Conference doing a little thing with Wukash, where he asked him like, what was the one OS feature that you would like to have that you don't have right now? And Ryan said, I would like to have user level int3. And it's like, what is that, right? And that underlies this entire thing. So what happens is, in the CPU, right, there's this thing called the interrupt table, or there are things called interrupt tables in CPUs, right? And the reason for this is right at the beginning. This is in like 8086. Like the original 8086 chip has this. This is not like a new thing. They've been upgraded over time to have different capabilities, but generally speaking, this exists for a very long time. So they have these tables because what you often want to do is you wanted to have some kind of like higher level supervisor, higher level's the wrong term, supervisory system level, should I say lower level code, operating system code, whatever. You want to have some code that you can trigger from anywhere instantaneously, meaning you don't have to like know in advance that you were going to use this code at this time, right? A call is when you know you were going to use it. At this point in the code, I call this function, right? This is like, we have no idea what we're going to do. We just suddenly have to do it. And one of the big reasons for this originally is like servicing hardware. So the CPU has to read something from some bus on some hardware, you know, like the original keyboard input or whoever knows what's happening, right? And so what would happen is an interrupt, literally the reason it's called an interrupt, int3, interrupt 3, an interrupt would happen that stops the normal execution, what the CPU was doing. It looks in a table for what it should start doing, it goes and does that, and then it resumes back to wherever it was in the program. It's literally what it sounds like. It's an interrupt. And this was used for doing things, like I said, like reading hardware and stuff like that, because bytes would like come into the CPU that it had to like look at right now. So it would stop the program, you know, this is back when you didn't have multiple cores or anything like that, right? Stop the program as it's executing right in the middle of whatever it's doing, go service this interrupt. It's called servicing the interrupt, right? Go jump to that code, do it, right? So what an interrupt really is it's basically, it's the same kind of thing as a function call, but it's one where you didn't know what was going to happen. It's a function call that happens out of nowhere. And the reason that this is very useful for something like debugging is because one of the things that a function call will do, right, is it's going to save what the instruction pointer was before it does the call. So it will put the instruction pointer onto the stack, right? This is a call instruction. We'll put the instruction pointer onto your program stack. It then transfers control over to whatever the location is you're going. So it changes the IP to point to whatever the function is that you wanted to call, does that, and then when it goes to do a return, it will pop off the stack whatever that instruction pointer was. So it's basically a thing that uses your program stack, your standard program stack, to track where you are in the program. That's a normal function call. An int can't do that because it doesn't even know if there is a stack. It's happening in the middle of any code. There may not even be a stack frame. You may not even be using the stack pointer as a stack frame at that time, technically, in 8086. So what it has to do is do some special work to preserve, right, like the IP in this way that will, like, we know we can preserve just what the instruction pointer is. Then we're going to go into whatever, we're going to look in this special table that the CPU literally has a hard-coded register that tells it where it is. So it's separately stored, right? We're going to go there, look up where we should go. And by the way, nowadays, we also look up a bunch of information like whether we should be transferring control to like a different level. Like, should we be dropping down to ring 0 from ring 3 and all this other stuff, right? So there's a whole bunch of crap in that table. And off you go. So the way debuggers are written currently, because they have to be, is on something like Windows, they are written as a user-level application. Which is fine, because that's roughly what you want. You don't want your debugger to crash to take down your whole system, right? You don't want CrowdStrike happening here, right? So you want the debugger to be running at ring 3 on Windows so that it's running up like a normal program, and if it screws up, like if Ryan on like the one bug he has, right? If you hit that bug and it crashes your system, you just want the debugger to crash. You don't want your whole system to blue screen. So it's good that it's doing this. But the problem there is it needs to do all the things that Ryan just says. It needs access to the memory. It needs to be able to put in like these things like int3s that will happen. And the problem is when you are at user level, right, the kernel doesn't want you doing stuff like messing with the interrupt table or, saying that you're going to be the person who gets whenever an int3 happens on this core, that you're the one who's going to get it or whatever, right? It didn't want any of those things for security and stability reasons. So as a result, the debuggers have to do all of the work that Ryan described through an API that the kernel will then use. It takes your API calls and goes, oh, I see. You wanted me to tell you when this guy hits an int3. So you go, I'll let you access his memory through my memory mapping APIs. You go, you poke it in there, you poke your int3s wherever you want, great. When the int3 gets hit, the kernel's the one who's going to get called, not the debugger, and then it's going to go through the API to let the debugger know that it happened. What this means is that now all of these things Ryan's talking about, every one of these traps that gets hit, is a full round trip. Debuggy is running at ring 3. The trap gets hit, the int3 gets hit. It's got to drop to ring 0, wakes up the kernel. The kernel goes, wait, what is happening? Oh, right, this is a debugged executable. I know I should tell the debugger about it. Okay, let me re-switch the task over to the debugger's context. Let me wake up the debugger in ring 3 and resume execution of a debugger thread to handle this. The debugger then goes, what just happened? Oh, the kernel told me I had a trap. All right, let me go fix up the trap things. Let me set any new traps that I need, and then let me retell the kernel back at ring 0 to resume the debuggy. Back we go to ring 0, it then switches in the context of the debuggy, back up to ring 3, and we resume where we were going, right? This is wicked frickin' slow for so many reasons, right? And so what Ryan was talking about is, hey man, what if we could just set the int3 to just jump to something in the actual, the person who's being debugged, that program? The debugger could like JIT compile some code that just does the trap operation that it wants to do and resets whatever it needs or anything else, right? Checks conditions, anything it wants to. We just set the int3 to not do any of that. Don't tell the kernel, don't take a rin transition, just jump right to that thing, do the stuff, and then resume. It would be so much faster. Getting rid of that, like, first ring transition, back up ring transition, back down ring transition, back up ring transition, right? It gets rid of all of that. So that's what he was asking for, and this would be like a huge feature. If there are any kernel devs out there watching, please add this. User-level interrupt handling like this would be so useful. And then that thing, if it actually wanted to do that huge transition thing, can just have a syscall that it does called actually transfer control to the debugger, right? So anyway, whole big thing of coolness there. We can't do
All
it.
I got from that is horse and debuggy is slow. That's what I got, Casey. So,
I tried so hard, Ryan. I tried so hard.
TJ,
but actually
TJ
makes
also
sense. I
tries
just
hard.
wanted
That's
to do
the
that
problem.
pun. Sorry.
Anyway.
Yeah, like one example of, so at a high level, what you might imagine doing in a debugger that uses that sort of where you want that kernel level feature would be if you set a breakpoint on a particular line of source code. If you like run your program within the debugger, you say stop here. That's like reasonably fast because those two transition or 3 or 4 transitions actually. You pay that cost once, and at the scale of like, oh, run to this line, it's not really noticeable.
And you wanted to come back to the debugger anyway, so it's like doing what you wanted, roughly, right?
Yeah. So when you actually really have to pay that cost to a sort of prohibitive degree in many cases, is when you wanted to say, stop at this line of source code, but only if this condition is true. So conditional breakpoints are like super common debugger feature. And it's like kind of the first version of fancier stuff that a debugger would want to do. But this is where it gets really slow, because then basically the debugger can't like do this installation of code that checks the condition inside of the debuggy. And so what has to happen is it hits the int3, controls transferred back to the debugger checks the condition, it evaluates some expression, it like does whatever evaluation stuff it needs to do to check the condition. And if that condition is false, then it goes back to the debuggy. And so if you imagine you put this in a loop that's supposed to run 1,000,000 times, maybe it happens instantly, normally, but because you're paying this round trip cost every single time the thread hits that int3, it just becomes like prohibitively slow. Now, if you're doing it once per frame, like it's still worth it for debuggers to have conditional breakpoints today, but they're like dramatically pessimized just from this problem. But if that problem were addressed, you could start doing lots of other things. Like another thing, something like printf debugging is profiling, like inserting profiling markup into your program. Like if you wanted to say, oh, I want to sample the time here, let me measure that, build me a flame graph of this kind of thing. That is the same problem as print debugging, where it's like, okay, go back to the source code, insert the things that I was looking for, build the program, run the program, get back into the state that I wanted to be looking at, and then inspect the log. And then it's like, oh, I need to drill one layer deeper into this like flame graph here, but I didn't add the markup there. So let me go back to the program, add the markup there, and you can't do it too much. You can't do it at every function, for example, because then that profiling cost will start adding up like dramatically, and then you won't even be able to see what the actual performance costs were. So what the debugger could do is like let's just do that dynamically. In the debugger, let's say, add a line of markup here, like a sampling line here, add a sampling line here, and then it could gather that data completely dynamically. It'd be way faster to like drill down into problems when it's really uncertain what you need to be looking at, basically. So yeah, that's like the high level, what you would expect as the user if you had this kernel level feature, basically.
Yeah. And so what we have to do now, basically, right? If you want to do this kind of thing, you can still do it, but what you have to do now is you have to handle a crap ton more edge cases, basically. So what happens is, if you want to, you can still do effectively this by not using int3, right? Because remember, the important part about int3 is it's a 1-byte instruction. So even if it's overwriting another 1-byte instruction, it's okay. All the code will still work exactly as it should because you only have the int3 just exactly where it needs to be. And anyone who's like jumping to the byte immediately after that, doing something weird or who knows what, it's fine, right? However, if we wanted to implement a feature like this without the assistance of int3, or halt or any of the other instructions that go through a table and are 1 byte, right? There aren't very many. I think there might only be those two. I don't know if there's a third one, but anyway. On x86 anyway. So if you want to do that without this, and Ryan has looked at this sort of stuff, and this is the kind of thing people are currently doing, so this is how you have to do it, you have to input some kind of a jump or a call actual instruction there, which takes more than 1 byte. So you can still do everything we just said, but you have to overwrite the thing you were going to overwrite with several bytes, potentially. And when you do that, now you run the risk of, if those several bytes overflow and go into the next instruction, that could have been instruction that someone was jumping to. So now we have to do all this checking to figure out, like, is someone jumping into the place that we had to overwrite to, and blah, blah, blah. So now what should have been a very straightforward extension of just patching in an int3 and everything works perfectly, and guaranteed no problems, what should have been a perfect extension of that is now this huge, like, did we catch all the corner cases? Oh, crap, it doesn't work in this one place. And now we got these bug reports from these guys who were doing this thing. And, and so if the kernel could just add this feature, all of that complexity goes away. And there's, like I said, so this is a thing that people have done. It's not like you can't do it. It's just it turns what would have been a very simple problem into a very complicated problem. And so that's why it would be great if the kernel could do it.
Hey, is that HTTP? Get that out of here. That's not how we order coffee. We order coffee via SSH, terminal.shop. Yeah, you want a real experience? You want real coffee? You want awesome subscriptions so you never have to remember again? Oh, you want exclusive blends with exclusive coffee and exclusive content? Then check out Cron. You don't know what SSH is? Well, maybe the coffee's not for you.
Terminal coffee in hand, live in the